Hey everyone, today we're going to talk about Gauss's law. Here on the left we have a portrait of Carl Gauss. Now he was alive in the late 1700s to mid 1800s. He was primarily a mathematician. In fact, if you ask your math teachers, a lot of them would say their favorite mathematician is Gauss. Okay, but he did dabble in physics, and he did make a pretty big contribution here with his namesake law, Gauss's law. Okay. An interesting fact about Gauss is him and a local physics professor, Wilhelm Weber, together built the first electric telegraph. So that's a fun fact for you. When we talk about Gauss's law, we first introduce the concept of electric flux. Okay? Flux is an old English word that means flow, and so really what we're talking about is the flow of electric field lines. So let's go ahead and get some electric field lines here. Now we need to know what these field lines flow through, and so we have to define a surface here. Now I've just called this an arbitrary surface S, and we'll talk more about that later. But now we're ready to define electric flux. So electric flux is the amount of electric field that penetrates a surface. Okay? So let's zoom in on this surface and see what's happening here. So when we zoom in on the surface, we have this patch of area here, and we can draw the electric field vector through that patch, and we can label a normal vector, namely a vector which is perpendicular to that patch of area. We call this the differential area vector, dA. It is perpendicular to the surface, in other words, it is normal to the surface, and so its direction is n hat, the normal vector direction. Okay? And it has a magnitude of the area of the patch, right? And since it's a small patch, we have that magnitude labeled as dA. Okay? We can see that in general these two vectors make an angle theta with respect to one another, and that will become important shortly here. For our definition of the electric flux, mathematically we say that a small bit of electric flux, d phi, is equal to the dot product of the electric field and that differential area vector there, dA. Okay? And so in principle, we have to integrate this expression over the whole surface in order to calculate the total electric flux. Now, the units for the electric flux in SI units are newtons per coulomb times meters squared. Let's take a look at some simple examples where this integral expression is actually very simple and we don't actually need to do any integration. So here we have a nice uniform electric field and a small little rectangular surface with area A, and its normal vector is oriented so that it's parallel to the electric field. So if you're thinking about dot products, right, there isn't going to be an angle between those two vectors. And so what we get is that the total electric flux through this surface is E times A. Now this is a maximum amount of electric field that flows through this rectangular surface here. If we were to rotate that surface 90 degrees so that the normal vector is perpendicular to the electric field, well then we can clearly reason out that there's no electric field penetrating that surface, right? And so we could conclude that the electric flux is zero simply by looking at the picture, right? But if you want to think in terms of the dot product here, the dot product between two perpendicular vectors is always zero, right? And so no electric field flows through the surface in this case. Let's take a look at an example where the plane or the rectangular surface is making an angle with respect to the electric field here. So we can see that the normal vector in hat makes an angle theta with respect to the electric field, and therefore when we do the dot product, we'll pick up a cosine theta there. So it's the electric field magnitude times the area times the cosine of that angle theta there. Another way to think about it is to think in terms of the components of the electric field, which are in the same direction as the normal vector and perpendicular to the normal vector. So we can clearly see from the picture that E cosine theta is the component parallel to the normal vector, and that's why we see the cosine theta in our final expression there. And we can also see that the e sine theta component is perpendicular to the normal vector, and that's why we don't see the sine theta. Now let's take a look at a simple case of a closed surface here. Now I've labeled a closed surface here, S, and we want to take a look at some patches of area with with differential area vectors dA. Now the nice thing about looking at a closed surface is that a closed surface has an inside and an outside. So we can make a convention here. We can choose, all of us together, that the normal vector is always pointing from the inside to the outside of the surface. And we can do that for a closed surface, but we can't do that for an open surface, right? By definition, a closed surface has an inside and an outside, but an open surface, there's no such thing, right? Well, this allows the normal vector to be determined uniquely for a closed surface. If we all have the same convention, then there's only one direction for the normal vector, and that is from inside to outside. So this means that we can redefine our total electric flux through a closed surface as the closed surface integral of E dot dA. This little circle in the middle of the integral sign is closed. That's why we say closed surface integral. Okay, so let's take a look at a simple example now of a point charge. Let's use our new definition for the total electric flux, namely the closed integral definition. So we need to define a closed surface. Let's use a sphere of radius r to do that. When we do that, we can label the radial unit direction r hat here, and we can reference the electric field direction and the differential area normal vector direction to this vector r hat. Okay, so let's zoom in on a patch here on the surface and draw that little patch and put the normal vector there, dA. Again, it has magnitude dA, which is the area of the patch, but its direction now is in the r hat direction. So for a sphere, the normal vector is always radially outward. Okay, you can think about yourself on planet Earth, right? Earth is a sphere, and if you remember back to last semester when you talked about normal force, right? The normal force always points up and away from the ground, right? So you can think of that as pointing away from the Earth. All right, what about the electric field vector? Well, the electric field has a magnitude E, right? But we know for a point charge that it's pointing radially away from a positive charge, right? So the r hat direction comes in again. So we can clearly see that E and dA are parallel no matter what patch we choose on the sphere, right? Just in general, E and dA are going to be parallel here on the surface of this sphere. We also know that the electric field is constant everywhere on a sphere once we choose a radius r. Once we choose a distance away from that point charge, no matter where we are on a sphere of that radius r, that point charge has the same magnitude for the electric field. Well, that's nice because we're going to have to do an integral, and so maybe our electric field just kind of pulls right out of the integral, right? Well, that is the case. We have everything is parallel, kind of like the case where we had that rectangular sheet with area A, and the electric field was parallel to that normal vector for that sheet. Well, it's the same kind of thing here, except everything is round. We have this sphere instead of a sheet. Well, so that means that the electric flux here is simply the area of that sphere times the electric field magnitude. That's nice and easy, just a product of the surface area of the sphere times the electric field. So 4 pi r squared is the surface area of a sphere, and then we just use E for the magnitude of the electric field. Well, let's go ahead and fill in the gap here. The electric field can be written as 1 over 4 pi r squared times the charge divided by epsilon naught. Now you may be familiar with the point charge formula kq over r squared, right? But we can always rewrite Coulomb's constant k as 1 over 4 pi epsilon naught. And I've gone ahead and isolated the 1 over 4 pi r squared because I think we all recognize that we're going to have some cancellation here, right? So we conclude that the total electric flux is simply the charge divided by epsilon naught there. So that's a really profound result because what it tells us is that the electric flux does not depend on the size of the sphere. So we could have drawn a really tiny sphere or a really big sphere and we would have gotten the same answer, Q over epsilon naught. Alright, so that's very profound, and this is the result that Gauss recognized and why this is called, why we study Gauss's law. Okay, so let's take a look now at this similar situation here where we have this point charge and we've drawn the electric field lines around the point charge. Well, we can draw that same sphere again. I've called it S1 here and I've labeled it in blue. Well, we just did this problem, right? If we were to calculate the total electric flux through this sphere, well, we would get the same answer, right? We would get Q over epsilon naught. But now I want to take a look at a slightly different surface here. I've kind of deformed, imagine we take the sphere and we kind of pinch it in the middle and kind of form this potato-shaped surface here in black labeled S2. Well, if we look at the electric field lines, all 6 of them still penetrate that surface S2, just like they penetrate the surface S1 there. And so, again, I think we can conclude that we have the same electric flux here. Remember, the definition of electric flux is the amount of electric field that penetrates the surface. And so we should get the same answer here for these 2 surfaces because they enclose the same charge. Well, that means that the electric flux is independent of the geometry of the closed surface. So that is, again, a really profound result that Gauss figured out. Okay, well, here we have, again, this idea of a point charge with the electric field lines there, and we've drawn kind of this crazy-looking closed surface around it. What do we get for the electric flux? Well, we're going to get Q over epsilon naught here. Okay. But how about a surface like this? Now this is completely new. We haven't seen this yet. This is a closed surface where all of the electric field lines both go into the surface and go out of the surface, right? So what do we do in this case? Well, if we take a closer look here, we see that every field line that goes into the surface also goes out of the surface, right? So they go in and they go out, and that's true for all of the electric field lines that penetrate that surface. So they penetrate in and then they penetrate out, right? And so what we can conclude from this is that there is no charge inside the closed surface, and therefore the electric flux must be 0. All of the electric field that goes in also goes out. So we're ready to state Gauss's law in its entirety now. And so what we have here is that the total electric flux through a closed surface is always equal to the charge inside the surface divided by epsilon naught. That is always true, okay? So let's take a closer look at the symbols and remind ourselves what everything means here. The circle around the integral there means that it is an integral over a closed surface. S here is the closed surface that we label S, and that is a surface that you get to choose. You are free to choose that surface. So in some cases, you want to look at the, well, in all cases, you want to look at the symmetry of your charge that you're trying to solve for the electric field, and choose a surface which has the same symmetry. Okay, and if you choose another surface, you could still get the same, you will still get the same answer, but it'll be much more difficult to do the integration. E and dA are kind of a combo here. So this is the electric field at the surface where that element dA is located. And dA is that surface area element there, which is normal to the surface. And then here, Qn is the total charge inside the closed surface, okay? And so sometimes you have to sum up all of the charge inside your closed surface if you have a bunch of point charges, or if you have a charge density. And then the right hand of this expression becomes an integral, where you have to integrate over the charge density so that you can calculate the total charge inside your closed surface. Okay, well, I hope that helped you guys understand Gauss's law. So this is where we're going to end the video. See you guys in the next one.